All right, I think we'll get started now. I'd like to welcome everybody to the fourth in this series of WGISS Technology Exploration Seminars, or webinars in this case. Today, we're very pleased to have Dr. Peter Baumann, who's the Managing Director of Rasdaman, and he's going to be talking about the coverage standards from the Open Geospatial Consortium, or OGC. And the coverage standards in particular is of timely interest, if you'll excuse the pun, because we're now hitting this big data deluge, which includes data in all spatial-temporal directions. And the OGC coverage standards are essentially the OGC attempts to satisfy or to solve part of that problem. And it's been evolving fairly rapidly for standard suites, particularly in the web coverage standard area. And Peter is going to basically give us a little bit of a tour of those OGC coverage standards, and particularly how they relate to spatial temporal data cubes as we attempt to solve this big data problem. And so with that, I'll turn it over to Peter. Thank you very much.
Well, thank you very much for this kind introduction. So I'm Peter Baumann, and I'm sitting actually in Germany there. This also gives me the opportunity to say a big thank you to Jennifer for really facilitating that excellent setup here, which allows us to convene virtually. So here we go, and I guess you should see the screen now, which starts with a motivation that shows the situation that we all know so well and that we don't like. We have lots of files, and we have them in archives with some cumbersome archive structures, and all of that is not really good for users to see. I was attending a presentation recently where some archive provider said, we have 3.7 million products available. Now, our users, I guess, do not want to get lost in 3.7 million themes. Actually, we know how to do better. Since last millennium, we know about seamless maps, and we have done that. And that has been propagated first by Google, and then by others as well. And suddenly, we don't have 3.7 million themes, but we have one object, that is the Earth surface. Okay, what now if we continue the same along the time dimension, and maybe also along the height dimension? That means we would get three-dimensional or four-dimensional cubes, and these cubes have some distinct advantages. Number one, homogenization. All the work of preparing them into one object is being done by the provider, making it so much easier for tools and for humans to drill through them. Number two, we suddenly get the same quality of service along the temporal dimension that we used to have along the spatial dimension already. It's all the same. So we would end up, say, with one data cube per satellite instrument. And then, of course, we will want to mix and match those data cubes as well. Okay, obviously, we are going public with these. So the question is, how can we provide these in a way that they are interoperable? And this is where the standards come in. Actually, we need to talk about data and about services and the quality of service that can be offered. Now, the term coverage has been set up long ago, long before my time actually, and that term tries to unify different kind of things, raster data like sensor feed, like simulation data, but more of them into a homogeneous object type called coverage. What do we want to do with those coverages? Well, we want to look at them, of course. We may want to mix in other data. And then there is another interesting use case that actually some other machine generates a request to our coverage server, and there is no human holding hands. That means we have to have enough semantics so that these two machines can talk to each other flawlessly. And that actually allows us then to be in the middle of a processing chain rather than just at the end, how the visualization tools do that, like web service, for example. So this actually is part of a bigger picture in OGC sometimes people complain that there are so many standards, but on the other hand, one big monolithic service standard would not help us either. This world is simply too complex to squeeze it into one spec. And so we find, for example, sensor observation service, which is excellently suited for upstream sensor data capturing, bringing that into some canonical shape, which then can be served downstream via, for example, web coverage service for access and for processing. Excuse me. So this actually naturally shows the analysis-ready data come in, something homogenized and pre-processed in a way that users can access and process these data in a versatile way. Okay, so what is a coverage actually? The term is a subtype of feature actually, so feature being some geographic object in OGC and ISO terminology. Coverage, you can see it like a space-time varying phenomenon, and if you find this too abstract, then just think about it as some spatio-temporal grid that can be regular or irregular, point clouds, or general meshes. So actually, the datacube world, which resembles the regular and irregular grids, is just part of the story. This is what I tried to express earlier. But today, actually, we mostly focus on the gridded part. And naturally, these grids are the big data part in our current holdings, what we have in our archives. So let's look closer at that. We have an abstract definition that is OGC Abstract Topic 6 that is identical to ISO 19123. Abstract means it describes general concepts. It's not a guidance to implementation. Sometimes you find people saying, I have based my implementation on ISO 19123 and therefore I'm interoperable. That is wrong. The concepts are too abstract to ensure interoperability. This is why OGC has paired this with the coverage implementation schema, which is a data structure that is also based on 19123, but it defines something that is detailed enough to be interoperable down to pixel level. So we can conformance test a server down to pixel level whether it does the right thing. Actually, ISO likes this specification as well, and so it's currently in the final stage of adoption as 19123-2. And 19123, which actually dates back to about 2000, it's being revamped currently, being brought up to speed, and then will become 19123-1. So we have two companion standards on coverages. If you look now into what these coverage types resemble, then you find on the right-hand side the green boxes with the grid. Several grid types have been established in the past, and today actually with CEOS 1.1 we have a general grid definition which encompasses all these plus a few more cases that have been detected over time. And this is actually what is the data cube. However, coverages can be something else. They can be multi-point coverages, that is point clouds, or they can be multi-curve, surface, solid coverages, and that is what we mean with the general measures. Frankly speaking, the left-hand side is not very much explored today. The main focus always is on the right-hand side, the coverage grid parts. Okay, if you look at a coverage definition, mathematically, a coverage is just a mapping from space to some value set. So if we store a coverage, we need to resemble the domain and the range of that function. The domain set tells us where do we find data. The range set tells us these data, so the pixel payload, if you will. Additionally, a coverage contains a range type which defines the data structure of the range set, so the semantics of the pixel type. That is not just something like integer or float. This is much more. It contains information about the semantics. So is this radians or is this something else like temperature? It tells about unit of measure. It tells about null values, accuracy, etc. This is actually taken from the standard sensor web enablement, and therefore we can carry over sensor data into coverages as shown in an earlier slide. So this triple pretty much defines the coverage. Then we have an extra slot that is metadata. These metadata are actually application specific. Nothing is defined about them. You see a definition of any there. So you can carry along whatever you want. The coverage will not understand it, but the coverage will duly transport it. And this way you can keep connection, provenance, and whatever information you want to have with your metadata. If you encode this, you can do that, for example, in GML. And here you see an example of a GML coverage. If you look at the text, you will find under general grid coverage as root the domain set, where you find a grid definition, and you find the axis and coordinates. You will also find a range set, which contains the actual values. And you find a range type. And again, you see here under this definition of panchromatic, you find a URL to the definition of it, and you find a unit of measure of the values that are contained in the range set. Good. You say you don't like GML, but you prefer JSON. Okay. So here comes the same coverage expressed in JSON. You still don't like it? Okay. We have on stock RDF triples. This is a small part of what it would look like in RDF. But the information content overall is identical. So the message is you can encode a coverage in different ways, and this encoding is canonical. We can make sure that the information is contained properly. Wait a moment. That holds for formats that can express it, like the ASCII formats shown that are informationally complete. However, of course, we want to have these big beasts in efficient binary formats. Therefore, mappings are defined, and these are also standardized. How to represent a coverage in GeoTIFF, how to represent it in NetCDF, etc. Okay, now these binary formats are efficient, but as we all know, they cannot carry along all metadata, and at least not always in the same way. So we have a problem here. We can be complete and inefficient, or we can be incomplete and efficient. Of course, we always want to have both, the best of both worlds, and therefore multipart encodings have been established, where you have some container that tags everything together, and then there is a header file that gives the canonical information, let us say, in GML, for example, or in JSON, but the big parts are factored out into further files. Such a container format can be multipart MIME, as we use it in emails with attachment. It can be zip or any other suitable format that may or may not compress. As we can have several such files with binary content, actually this also allows us to express tiled coverages, or we can have collections, and even we can do streaming with it. So this shows you that we have a couple of encodings available. You can pick an ASCII format, you can pick a binary format, or you can pick a combination in some multipart encoding. So much about the service. And now the next thing is about the services. That was the data, now the services come. The web coverage service is naturally made for expressing service requests on coverages. It's not the only one. You also can use a web feature service, for example. Remember, coverage is just a special type of feature. But with a web feature service, you would get just the whole coverage, which is not what you typically want. With a web coverage service, you have bespoke functionality specifically trimmed for coverages. The core specification, which every implementation must fulfill, simply gives you access to spatio-temporal coverages or subsets thereof. So subsetting can mean trimming. It keeps the dimensions, so two-dimensional cutout from two-dimensional coverage. Or it can be slicing, where you reduce the number of dimensions. So in this datacube example here, you could extract a time slice as one horizontal scene, or you could drill through, get the pixel history, so a one-dimensional result. This all you can do with the core, and then finally you can request a particular encoding. A large number of implementations exist meantime on client and server side that support it, both on open source world. So a couple of weeks ago, I assisted GDAL in transiting from WCS 1 to the current WCS 2, but also commercial tools like, for example, S3 ArcGIS starting in version 10.3 supports WCS 2. So that is the core. Now we also have extensions available that provide optional functionality facets. In other words, an implementation does not have to support it. There are various extensions available. I'll come to that in a minute. But first, let me add that we also have application profiles, which are bundles of specializations for particular purposes. We have one in place for Earth observation currently, and there is another one in the make for Med-Ocean. So on the next slide, you see the big picture that puts all of that together that we have seen so far. On the left-hand side, you see the data standards. Centered around the coverage implementation schema, you find various encoding. On the right-hand side, you find the service part with a WCS core, and that is mandatory. And then the various service extensions that add some additional functionality. You also find protocol binding extensions that allow you to encode the request in whatever is your favorite web protocol. So all functionality is supported on all protocol bindings, and therefore implementers and users can choose freely which one to support. Let's look at a few extensions. Wait, wrong. First, let's look at the coverage core itself. So remember, we can download part or a coverage as a whole. By the way, with the values guaranteed unchanged, unless you use some lossy compression, of course. So as opposed to a web map service where you get an image, here you get the data, like elevation, for example. If you want to do a cutout, then you indicate that per axis. The subset parameter allows you to say, for example, in longitude, we want to go from 100 degrees to 120 degrees, in latitude as well, and along time we do a slicing. So effectively from this three-dimensional image time series, we are extracting one image slice with this request. If you want to have it encoded in a particular format, we can indicate so, otherwise we would get it in the native format as stored on the server. So that is the core. Let me put special emphasis on one thing that is frequently an issue of discussion, that is the handling of coordinate systems. Each coverage has one coordinate system. Everything else would just be terribly complicated. This is called the native CRS, and it is the one as stored in the server. You can see this when you retrieve the coverage because there's an attribute named SRS name that actually contains the identifier of the coordinate system. In the example, in the yellow box, you find an SRS name where you find actually a composite CRS. There is EPSG for 326, so that's WGS 84. This contributes the first two dimensions, lat and long. And then there is time added as an extra axis. And so the compound CRS effectively has three dimensions. The axis labels could be deduced by looking at the definition, resolving the URL, but for efficiency, it's repeated here. We have lat, long times measured in degrees, and days. And in the lower and upper corner fields, actually, you find the concrete coordinates. Actually, the list of CRSs supported by a server can be obtained in the capabilities document of that service. Look at the CRS supported tags, and you find what the server can do for you. Whether it knows, for example, about time coordinates or not, whether it supports EPSG for 326 or not. Okay, so that's it about the coordinate system handling. And now let us look at a particular extension. I picked this one, the range subsetting, because it's very necessary. It allows us to extract bands or variables from some hyperspectral image, and also because it shows a very simple principle by just extending the number of parameters. It's still a get coverage request, but actually we have a range subset parameter now which indicates which bands we want. So we can extract red, You can extract a false color image by saying NIR, red, green. You can actually invert the sequence if you want green, red, blue. Now, if we have a large number of channels, maybe we don't want to enumerate them, but indicate an interval. And of course, we can combine all these principles. So all of that can be piggybacked into a get coverage request, and so you get only those bands from the server which you actually need. No extra transport. Another type of extension is WCS PE4 Transaction. This allows to modify coverage offerings on a server via web requests, and that does not extend get coverage, but it adds new request types. Actually 3 of them: insert, delete, and update coverage, including partial updates. This is designed in a way that what you extract from one server via get coverage can, for example, be inserted readily into another service via insert coverage. You can build mashups of services. The principle is shown here. You have a request type with name insert coverage, and you give, in this case, reference to a netcdf file. The server will fetch that, will insert it, and will generate a new identifier directed by the use ID parameter. Okay, so this shows us another type of extensions. And the third and last one, which I want to bring to your doors, is the WCPS, the Web Coverage Processing Service, which simply speaking defines a spatio-temporal datacube analytic language. All the screenshots you see here have been taken from WCPS results, actually. Just to give you a flavor of it, if you want to look into 3 MODIS scenes, M1, M2, M3, want to get the difference between 2 bands, we can express that by having a for loop. $C is bound in turn to the 3 coverages. You do the difference, encode it in TIFF. And if you want to do server-side filtering in addition, you add a where clause that expresses a predicate on the pixels. So what you do is data search as opposed to metadata search, and you do filtering and processing on the server. Actually, you can also do data fusion. There are many things that are possible, but this webinar is not about WCPS in particular. There are webinars on YouTube. I will give you links later if you're interested in that. Let me just add that this allows for massaging, for processing of data cubes that are both regular or irregular, or actually both, because we frequently see that ortho image time series are regular along space, but irregular along time, for example. Okay, here is an example of what we could do, say terrain draping. You construct a 4-band PNG image having red, green, blue, where we put in bands 4, band 3, band 2 randomly from some Landsat scene. And in the alpha channel, we put an elevation model. Okay, we have to scale that to adjust resolution, but then we can ship it as a PNG. And on client side, the WebGL can render this into a draped terrain, like you see from the screenshot in the background. So definitely WCPS is not a visualization tool, but you can obviously generate representations that are amenable to visual rendering on client side. Another example, WebMap service can be emulated. In this case, we have 4 layers, orthophotos, water lines, water areas, and a DEM again. And we just overlay them. So we have $P, the orthophoto, which is black and white, so gray color. We need to multiply it into RGB space. Then we have water lines, and we want to color them somehow. Water areas get a different color. And for the DEM, we have a case distinction, which does color coding, as you can see, highlighting, for example, the risk of flooding. And this is actually, by the way, how we do that internally in our implementation. All the requests of WMS, WCS, etc. are translated into a query internally. But having said that, this is really not what users want to see. They don't want to learn just another language, but they want to remain in the comfort zone of their well-known tools. So if you just want to do simple map navigation, you want to continue using Leaflet. Virtual globes, okay, use another Whirlwind. WGISS, use QGIS. And if you want to do high-end analysis, you are familiar with R and Python, so you want to use those ones. The good thing here is the standard WCS allows all standards conformant clients immediately to talk to all standards conformant servers. So this is an advantage of the interoperability. It's not just about server-side, it's very much also about utilizing all the wealth of clients available already. Okay, now so much about the concepts. Let me give you examples on how that is realized. And I will make use of Rasdaman being WCS reference implementation. So here is some screenshots about virtual globes, 3-dimensional and 4-dimensional one. This is a portal that capacitates very much on time series analysis, ESA Earth observation datacube. Then the European Center for Medium Range Weather Forecast, among others, offers river discharge and doing this a long time. And a British Geological Service gave us data where we could render actually stratigraphic layers below Glasgow. So this is what it looks like from 6 feet under. Or, as I mentioned, Jupyter notebooks allow you to use Python as an access language. And that is, again, something that is nicely documented on GitHub and on YouTube. One initiative that I would like to bring to your doors is EarthServer, which is establishing Agile analytics on image time series, 3D, and weather data, 4D, on Earth and, by the way, also planetary data cubes. We rigorously use Web Coverage Service and WCPS as the interface standards. And this way, it also demonstrates the usefulness of the standards and their scalability into real-life use cases. The largest installation, that is Mio, a small company in the north of Italy. They hold mostly Sentinel data, and that has exceeded 1 petabyte last summer. And whom else do we have on board? Plymouth Marine Laboratory is doing ocean color analysis. National Computational Infrastructure Australia is contributing land-to-date data. And the European Center for Medium Range Weather Forecast is opening their climate archive. And that is our next challenge, where we tap into their tape archive and we want to unleash their 220 petabytes. That's an exciting adventure. So we have started, we can already attach ourselves to the archive, but now the whole thing needs to scale, and we've still got some work to do on that. The whole thing is an initiative where Europe, US, Australia come together. And again, here's some links where you can get further information if desired. And one thing that I mentioned was federation. Hey, we have now with EarthServer different services. We want to combine data cubes. How can we do that? And that is something that I want to show quickly by switching to the browser. Okay. And Jennifer, please let me know if something is going wrong, but I hope this is getting across.
I can see your demo. I'm not sure if you're able to, you might want to minimize the mini control at this transition.
All right.
Drag it off the screen if you can, or close it out like we were done.
Somehow it does not allow me to move.
On the right-hand corner, right there, yes.
Yeah, but the clicking does not do anything. So unfortunately, it does not want to go away. Okay, maybe we can live with. Right.
Carry on.
Okay, so we have some query that we want to send out in order to find heavy rainfall risk areas. Now, it's about weather data, so it makes sense to go to the European Center for Medium Range Weather Forecast, and you have seen the path the query takes, because actually ECMWF has precipitation data, but they do not have Landsat data that we need. Okay, we see the result here, which happens to be mapped to a virtual globe. And in the background, actually, we see that a subquery has been forked to down under. It's really far down under, but zooming out will get it, and hooray, here it is. So actually, the query has been split automatically between the contributing participating partners. Of course, we can send the query to NCA right away. Now, they will happily dig out their Landsat 8 data, but oops, they don't have precipitation data. So they need to fork a subquery to do some of the processing at ECMWF. The result comes back, gets integrated, and hopefully will look the same. And in a second, we'll have it. And here is our result again. Now, what's the advantage of this? Two of them. Advantage number one is we just don't need to know where the data sits. We send a query to the Federation, and the Federation will do that, will negotiate that. And number two is that we suddenly can combine data from very different locations without thinking of it. So we can combine Australian and UK data, and we don't need to worry about any of the internal optimization. The system can do that efficiently. Okay, and with that, let me switch back to the presentation, as we have seen. And if you ask now, okay, and what is behind? Actually, as I mentioned, WCS reference implementation, we have our Rasdaman tool that stands for Raster Data Manager, and that actually is built on the paradigm of query languages. And the mother of all query languages, of course, is SQL, and extending that with multidimensional arrays. Underneath, we have a scalable parallelizing peer architecture that we call tile streaming. The whole thing is in operational use. You can get the source code from the Rasdaman.org site, and that actually is heavily parallelized and federated. You just have seen an example. And if you look behind the scene, actually we do an adaptive partitioning that can be regular, like many tools do that, but that can also be irregular to adjust for a particular axis pattern. Why do we want that? Well, look at OpenStreetMap and you find a similar situation. It's vector tiling, but still in central New York City. You want to have very fine grain and fast access, whereas in the Southern Pacific, you maybe can combine data into one big blue tile. So adaptive tiling definitely makes sense, and our benchmarks show that this is a good way to speed up access. In our case, we have this as a tuning parameter for the database administrator to configure the tiling, which then is followed further by the database engine whenever new data get ingested. It's important, though, that you don't see that on query level. In the WCS request, you didn't see anything about tiling. This is completely hidden. And this, of course, is a good basis for parallelizing internally, again hidden. We do that in a way differently from, say, MapReduce, where you have a fixed map and then a fixed reduce phase. We look at every incoming query individually, and so we find out that in this case, for example, the yellow query, we can answer right away because we have the data. The orange part we cannot answer, but we know somebody in the cloud who has that, so we send a subquery to that buddy. And that buddy actually just receives the query, doesn't even know whether this is from another cloud node or whether it's from a user. With the same principle, we can do the federation that you have seen by forking a query to another data center. And we can even do that on moving targets. We have been accepted by the European Space Agency as an onboard experiment. We will install Rasdaman on board the node there and then link it into the federation. The principle has been explored on more than 1,000 cloud nodes in Amazon. So that's a way of optimizing very individually the queries. If you say, oops, but that optimization takes a long time, actually no, we have measured it and it's about 1 millisecond on a regular CPU. Okay, so this was looking a little bit behind the curtain of what such a service could look like. And wrapping up, here is a collection of datacube standards that may be relevant. First of all, we have OGC, of course. We have the coverages data model, and we have the WCS service model, which are streamlined, which are in sync. The coverage implementation schema, so the coverage data model, is currently becoming 19123-2, the final stage of adoption. 19123 is under revision and will become 19123-1. After that, we will look at WCS, where ISO as well has expressed interest. Inspire, the European framework for common spatial data infrastructure, has also adopted WCS one-to-one from OGC. The coverage model has been adopted with a few changes. This is where we still are discussing. And then we have a completely different part, because what we have established with the SQL array extension has found the interest of the ISO SQL working group. And currently MDA is in the final stage of adoption, which will become part 15 of SQL, standing for multi-dimensional arrays. And that actually adopts the Rasdaman query language. Okay, this doesn't stop here. Actually, there is a lot going on in coverage world. It's very actively evolving. I mentioned the NetOcean application profile, which is under work, led by UK Met Office, also with participation of NASA. One important aspect is polygon raster clipping. You find that bounding boxes often are too inefficient. They transport way too much data, and you would like to be more accurate in specifying what you really want, and that can happen through a polygon, notably through a space-time polygon, like you want to have for flight paths of airplanes, for example. Data metadata integration in queries is an important step, and there is some work going on with the Athena Research Institute in Greece and others. And something that is on the wish list is asynchronous request processing. And maybe you have further ideas, or maybe you want to join us in writing the standards and fleshing out the specifications. Please feel very welcome and don't hesitate to contact me. Here's a page that I don't want to read to you. It's just a collection of links to resources, and that may help further after the webinar to drill into details. Let me rather conclude. So coverages are a paradigm that allows to unify data structures that resemble multidimensional rasters and other data as well. Through conformance tests that we have in place for WCS, we can guarantee pixel-level interoperability on these structures. Fortunately, we are converging towards a consensus across different standardization bodies, OGC, ISO, and Inspire, concretely speaking, and also along the major tools, open source tool and commercial tools as well. So that is, I believe, a good step towards interoperability. And actually, we got good feedback from people like ECMWF saying that web developers not having heard of standards before in the OGC world immediately feel at home with them. So for programming, for developing bespoke APIs or clients, it's not no magic, no excessively hard work to do. I showed you one particular implementation out of several existing, Rasdaman, which actually is technically speaking an array database system, which has shown scalability of the service standards in practical use beyond the petabyte. And with that, I want to close here. And thank you very much for your attention. And I'm very much looking forward to answering questions.
Okay.
Thank you very much, Peter. That was very informative. I know I've been working or maybe dabbling in the WCS area for more than 10 years now, and yet I still learned several things from this talk about what WCS could do that I didn't know before. So I'd like to open it for questions. You can type your questions into the Q&A pod. We found that that works better for this kind of interaction, and Jennifer will moderate the questions with Peter.
Okay, thank you, Chris. Our first question is your question. Has any work begun on the asynchronous request feature yet? Peter?
So concerning the asynchronous request extension that it will be, we first looked into WPS because that offers asynchronous processing, but after consultation with the WPS group and the OGC architecture folks, it turned out that this does not work, so we went back to the drawing board. And now we are open, actually, in terms of directions. PubSub is something that seems important and should be reflected somehow. But aside from that, we are looking for input.
Okay, thank you, Peter. Are there additional questions? If you have a question, just enter those into the Q&A pod. It works like a chat. Okay, we'll give this a minute or two. And while we're waiting for any questions, what I did want to point out is that if you look in the lower right-hand corner of your screen, both today's agenda as well as Peter's presentation are available for download. So if you click on either one of those two files, you will be prompted to download the file. And a YouTube recording will also be made available within a couple of days. Are there any additional questions from anybody? Okay. If there are no additional questions, then I will turn it back over to Chris Linus for final remarks. And with that, we will log off from the audio component, and I'll leave the virtual meeting space open an additional 10 minutes or so. Should you think of a question that you would like to ask our speaker, this way I can forward the Q&A log to him afterward. He can follow up with you offline.
So I'd like to thank Peter again. As I mentioned, this has been very educational for me and hopefully for several of my people that have also been tuned into this webinar. And I think, in fact, we'll probably be able to make use of some of the things we've learned today in the not-too-distant future. So thanks again, Peter, and we'll keep the Q&A pod open for questions as you think of them. Thank you.
Thank you very much, Peter.
Yeah. Thanks to both of you. Thanks a lot. It's my pleasure to be part of the story and to present here. And yes, I will remain present here until Jennifer closes down the show.